Maintaining an industrial facility is a constant negotiation with the power grid. Every time a heavy machine cycles on, it demands a massive, often violent surge of energy, and the facility engineer is the only line of defense between stable production and a total system blackout. This responsibility is governed by a hard limit, the sanctioned load. This is the absolute maximum macro-level capacity the local utility grid permits the facility to draw at any given moment. Auditing a plant requires mapping the entire journey of that electricity, from the high-voltage utility entry down through step-down transformers, and finally into the diverse loads of the factory floor. This single-line diagram illustrates the plant's primary bottleneck. Raw utility power enters a step-down transformer with a fixed capacity of 4,500 kVA. However, there is a discrepancy between the transformer's capacity and the machines it serves. The transformer provides total power, but the heavy inductive motors on the line consume specific active loads, such as these 22 and 50 kilowatt units. Transformers and servo stabilizers are rated in apparent power, kVA, while the mechanical work done by a motor is measured in real power, or kilowatts. Because industrial motors use electromagnetism to turn, they draw more total energy from the transformer than they convert into physical motion. Tracking the gap between apparent and real power is how an engineer prevents a facility-wide overload before a single machine is turned on. The gap between the power supplied and the power converted into work represents a significant inefficiency. Inductive motors must maintain a magnetic field to operate, and that field is sustained by reactive power. To manage this, engineers utilize the APFC, or Automatic Power Factor Control Panel. This 1800 kVA unit is installed in parallel to the main load. The APFC panel does not generate voltage like a solar inverter or control motor speed. Its function is localized support. The capacitor banks inside the APFC supply reactive power directly to the motors, eliminating the need to pull that specific current from the utility transformer. By fulfilling the motor's magnetic requirements locally, the APFC improves the system's power factor, effectively bridging the gap between kVA and kilowatts. This optimization frees up trapped capacity in the main transformer. It ensures that the facility can operate its heaviest machinery while remaining safely beneath its sanctioned utility limit. Beyond the macrogrid architecture lies the operational heart of the factory, the Motor Control Center, or MCC. This is where power is actively switched, routed, and monitored. In this environment, engineers employ predictive diagnostics to identify physical degradation before a breaker trips or a fire breaks out. Thermography lets us audit energized panels without stopping production. Normally, drives and terminal blocks sit at a steady, ambient 50 degrees Celsius. However, oxidized connections create localized resistance. This generates heat, manifesting as a thermal spike reaching 90 degrees or more. Components operating near the 100-degree threshold are in a state of imminent failure. The heat will melt cable insulation and lead to a localized short circuit. One common result of a burnt terminal is single-phasing, a scenario where one of the three power phases to a motor is completely severed. A motor that loses a phase will emit a violent acoustic hum. To compensate for the loss, the motor pulls an imbalanced, excessive current through the two remaining phases. Because standard overload relays are often too slow to react to this specific imbalance, a motor can incinerate its internal windings in under 3 minutes. Using thermal signatures to predict this failure is the only truly reliable way to prevent total motor destruction. While thermal scans catch external faults, we must also audit the internal integrity of the motor itself, specifically the copper winding insulation. This insulation degrades slowly over time due to thermal stress and moisture. As it weakens, microscopic amounts of current begin to leak from the windings to the grounded outer casing. The Megger test quantifies this degradation. By applying an electrical load across the insulation, we can measure exactly how much current is escaping to the casing. This audit requires a stable 500-volt DC source. Unlike alternating current, which fluctuates, a steady DC voltage provides the constant pressure needed to force a readable leak through the barrier. Using Ohm's law, we calculate motor health. With our 500-volt source, we look for a resistance of at least 1 million ohms, or 1 megaohm. At exactly 1 megaohm, the leakage current is 0.0005 amps, half a milliamp. Any measurement below this threshold indicates failing insulation. Measuring this microscopic 0.5 milliamp leak is the difference between a controlled, scheduled motor replacement and an explosive, entirely unscheduled factory shutdown. Even when components are healthy, the physics of starting a machine can destabilize the entire plant. When a 22 kilowatt motor is started abruptly, it can cause a voltage dip severe enough to dim the facility and trip every adjacent machine. To understand this surge, we calculate the motor's nominal running current using the three-phase power equation. We isolate current, dividing the 22,000 watt rating by line voltage and power factor. At full load, it requires 38 amps. If the facility is designed to handle a 38 amp draw, it seems contradictory that starting the motor would cause the entire grid to sag. The cause is the rotor's inertia. At the exact second of startup, internal components are completely stationary, meaning they aren't cutting through any magnetic flux. This stationary state means there is zero back EMF, the internal opposing voltage that restricts current. Without back EMF to resist the flow, the motor acts as a near short circuit. It violently pulls up to 6 times its weighted current, spiking past 160 amps, and completely starves the rest of the facility of voltage. Preventing this violent inrush surge requires moving away from simple mechanical switches and instead adopting dynamic, precise electronic control. The variable frequency drive, or VFD, allows an engineer to bypass the zero back EMF problem entirely. A standard start creates a 160 amp spike, placing immense stress on the grid. The VFD implements a soft start. By slowly ramping up frequency, it builds back EMF artificially. The motor reaches full speed while current never exceeds safe limits. This controlled ramp also provides a critical mechanical benefit. It eliminates the violent physical jerk associated with a sudden start. Preventing this instant torque spike reduces the wear on gearboxes and coupling shafts, significantly extending the operational life of the equipment. Industrial engineering is the precise modulation of energy, transforming the raw, volatile physics of the utility grid into a controlled, predictable tool for production.